100 million years now, we're starting to say like that's actually something that's like a decently long time scale. But as a result, we can't just sit here and say, I'm going to look at that galaxy as it evolves. I mean, I guess you can, but man, you're going to need good documentation because it's going to be a long time before that thing changes. Yeah.
What's up, you scholars of enlightenment? The James Webb Space Telescope is now science ready. And as well as producing some of the most beautiful and awe-inspiring images of our universe to date, it is also breaking scientific records at an incredible pace. So over the last week, we've seen JWST constantly observe galaxy candidates that are further and further away and capture possibly the oldest and most distant galaxies ever observed. So to help me to dig into those incredible observations, how they were made and what they can tell us and their wider implications, we welcome another fantastic special guest, Hannah-Laura Girling-Donsmore. Hannah-Laura, how are you doing?
Hi, I'm doing well, Sam. How are you?
Very, very well. How are the dogs? Have you got them under control?
We do have the dogs under control. It is a little bit of an endeavor. But I decided that today my usual technique of throwing them frozen green beans during meetings was just not going to work. So we have an entire affair set up with a fan and a TV show for them. So hopefully they will be entertained.
They get treated better than some conferences by the sound of it. It's pretty good effort. So for people watching, Hannah-Laura is a theoretical astrophysicist, and science communicator at CU Boulder, studying how supermassive black holes at the centers of galaxies grow. She also does all things SciComm, from starring in popular Netflix documentary Behind the Curve, to appearing on podcasts such as Titanium Physicists, to volunteering with Astronomy on Tap. So who better to help me dig into these recent observations and help me understand the ins and outs? She's also a Stargate SG-1 fan and a Sam Carter fan, so bonus points for that in my book. She is my favorite character in my favorite sci-fi. Give us a few words on that.
I love most sci-fi that develops in-world logic and an in-world science.
Yeah.
I don't
there's
love
actually
it
like a fleshed out universe that you can suspend belief and think maybe that could actually happen in the future sometime, maybe, rather than it just being sort of magic.
Yeah, I don't love it when it's all a black box. Like Stargate, Star Trek, that's a big one. I do have to say this before they come and take my Trekkie card.
Go on.
Big Star Trek fan. Just have to get that out there. But yeah, I didn't actually watch very much TV growing up, but then when I got to college, I started watching a lot of sci-fi, and Stargate was part of that. And it's a cheesy thing, but when you're a young woman and you're a physics major, and when you actually get further along in physics, in a physics major and then into grad school, I find that people are a little bit less weird about you being a woman, but certainly like your first year, people are weird about it. And so someone like Sam Carter, like that's kind of, you're like, okay, like this is great. This is good. This is, I'm not crazy. So
she was called Sam. Yeah. She was called Sam as well. So obviously I was, I was happy about that. I'm like,
I actually didn't think about that connection, but you know what? There you go. That's an easy.
Great.
You never get a Hannah-Laura. You never get a Hannah-Laura.
Well, maybe that's the next push for a character in Stargate. So let's get into the sort of madness, I guess, that's been going on this week. So what redshift are we up to now? Because it seems like the JWST has been throwing out these higher and higher redshift galaxies, potentially further and further away. It's been a little bit like drinking from a fire hose. So I checked in on this kind of on Monday, and we had the CEE RSJ 141946, all this sort of stuff, which was a Z of 14.3. They called it Maisie, or the cosmic potato. But then by Tuesday, we had this further away one from the Scottish astronomers, which was this Sears 93316, which was Z 16.7. So is that where we've reached yet, or did it continue to sort of spiral out of control while I've been doing other things?
This is a tough question because there's a lot of papers that have been coming out. And a lot of them, even for the same objects, and this is several objects, have different redshifts that people are measuring. And the reality is that we're not going to know what redshift we've gotten to until we can do some follow-up spectroscopy, follow-up observations that are more in depth. I've heard some pretty major numbers going around. I think the 16.7 is what a lot of people are willing to say. Yeah, I think that's about right. I think that's probably true. Not because the other papers are not compelling, but it's a situation of extraordinary claims require extraordinary evidence, and the more extraordinary the evidence needs to be. So I think 16.7 is something that a lot of people I've been talking to are not saying, I'm gonna wait. I'm gonna wait before I say.
They're like, that looks reasonably secure. What's the obviously this is going beyond the science into sort of conjecture, but what's the most extreme you've heard in these papers that people have tried to sell?
I've heard numbers pushing all the way down to, I think, 150 million years after the Big Bang. Wow. I've heard some pretty big numbers, or at least the possibility that that follow-up could find that.
Amazing stuff.
So incredible stuff. It
really is. So can you give people just a little bit of an idea, because they might not quite understand what we mean by these numbers, Z, the 16.7 and these kind of things, or even redshift. So we're talking about these things being so far away and moving away from us so quickly that they appear incredibly red to us. Is that basically the idea?
More or less. So if we think about in our daily lives, if you see an ambulance coming towards you and then past you, hopefully past you, hopefully it's
not just stopping right there, then we don't get the other side, unfortunately.
But going towards you and then past you, it gets louder and shriller as it gets closer to you, and then as it moves past you, it gets quieter and less shrill. That is called Doppler shift, and it's because when a source of a signal, a source of radiation, a source of a wave, is moving towards someone, it actually almost the emission of that wave actually kind of catches up to the already emitted wavelengths, and it effectively shortens them, which makes them higher energy. That is to say, shriller and louder. And then as it moves away, there's almost this stretching because you emitted a wave. You emitted some point of your wave right here, you moved over here. And so it's effectively, you're stretching out that wavelength, which is why it gets quieter and then it gets less shrill. And this happens to all waves, which all radiation is waves, because particles, waves, when you're getting down to that scale, it's all electromagnetic radiation. And in this case, we're talking about photons. And in the case of these photons, they were emitted from these galaxies, and they're moving towards us, and they're moving a really long ways. But what's actually causing them to redshift, like that ambulance moving further away from you and the siren getting quieter and less shrill, is the universe itself is expanding. And so these are moving towards us, away from the galaxy that emitted them. Well, that galaxy is moving away from where that wave, from the point when it emitted that wave. And so it's stretching that wave out. And so when it gets to us, when it was emitted, we even have observations, not necessarily from JWST right now, but we have observations of signals from high redshift. Well, what we used to call high redshift, I don't think we can call it that anymore, of photons that were gamma rays when they were emitted. And when they get to us, they're infrared, they're UV. And so they get to us, and that's how we're observing them. And they're redshifted, though, because red is a lower energy. Red is the lowest energy of the optical wavelength. So if it loses energy, it's redshifted. If it gains energy by moving towards you, it's blue shifted.
So how does that tally with distance and age? So this Sears 93316, I think they said it's 235 million years after the Big Bang, they believe. But 35 billion light years away, so more distant in light years than the age of the universe, which I think upsets a lot of people, and it sort of perturbs me a little bit, even though I kind of know what's going on. So do you want to maybe explain that to people, how this thing can be 13 and a half roughly billion years old, or maybe a little bit older, but it can be 35 billion light years away? Because I think people are a little bit unsettled by that. I know I was initially.
Well, you should be, because the universe is unsettling. But how this is working is, as I said, the universe is expanding. And so the galaxy that emitted this wavelength, these photons that we're observing now, it started off at one point, but it's in a universe that's expanding. And as a result, it's actually getting moved away from where it started off. And so that signal came to us when it was, let's say 13.5 billion light years away. As you said, might be a little bit more, but just, I like easy numbers.
Yeah.
And probably picked the wrong field then, huh?
Yeah.
But, started off there.
Physics was a poor choice in that.
Right. Oh, there is all that time.
Yeah.
But yeah, so it starts off, but then it gets moving away from where it was emitted. And it's expanding at the rate that the universe is expanding at. And so that's how you end up getting to, being more light years away from where we are than there are years that the universe has existed. Is that clear?
Yeah, that makes sense. So,
Okay, cool. All right, cool.
So the universe essentially is kind of expanding under its feet, basically, which means by the time this light has reached us, the universe has expanded, which means that the thing is actually further away than the time it took the light to reach us. So the interesting thing about this is how is this redshift calculated? Because I've seen all sorts of weird words in the papers, like bagpipes, like Lyman break features, these kind of things. I'm guessing because we have shifts in frequency, shifts in wavelengths, you're looking for kind of signatures that where they should have been, like a particular element gives a certain spike, and then looking to where they've shifted to. Is this kind of the idea that we're going with?
That is exactly the general premise of what we're doing. So specifically, the Lyman break is time to talk about quantum mechanics, actually. Okay, before we get to that, it's time for quantum mechanics.
Right, we row back a little bit and we'll do some concepts. All right.
With quantum mechanics, so to first order, you can visualize atoms as you've got your nucleus, which is going to be your proton or protons, and some number of neutrons, right? And then orbiting that nucleus are electrons. And I could spend an hour going into the details of why the shell model is technically not correct, but that is not interesting. And it's also a little needlessly pedantic. So you have your electrons, and they exist in these different shells. And that's actually the quantum of quantum mechanics, is just that they have discrete energy levels. That's all that means. Yeah. And you start off with your so there is the lowest energy distance that an electron can be from its nucleus. And then but the thing is that electrons are fermions, and fermions don't like to hang out with each other. And so you can only have two fermions in that innermost shell. Well, actually, you can only have so many in an innermost shell, right? And that has to do with their spin, which again, I'm going into the weeds, so I'm going to keep moving. Yeah. You can have them a little further out, and that's the next energy level. And then you can have them further out, so on and so forth. And there is this series called the Lyman series, where it's a series of emission lines, where if an electron drops from a higher shell to a lower shell, it loses energy. And if that seems weird, think about if you're riding a skateboard around a bowl at the skate park, and if you slow down, you're gonna go further down in the bowl. Yeah. And so it's just like that. If you lose energy in in your electron shell, you're gonna drop to a lower electron shell. But the thing is, energy is conserved. And so where does that energy go when the electron drops down a shell? It boots out a photon, and it boots out a photon of a different wavelength. And that's your Lyman series, is the series of emission lines from photons.
All these different energies and wavelengths of photons that correspond to the different jumps that can happen between those series.
Electron jumps.
Yeah, those electron
Exactly.
jumps, yeah.
That's exactly it. And so, but there is a limit to this. Eventually, there is going to be an energy of getting rid of the electron, ionizing you're ionizing things, you're booting the electron all the way out.
Yeah.
And that's your Lyman limit. And we know where that is. That's something that is not a mystery. It has grounds, both you can calculate
so
this
we can
on
measure we can measure that in the lab
Exactly.
and work out how much energy that takes.
Yeah.
We can also do it from first principles and work out, I can't remember, it was like, I can't even remember what the number is. It's like 13.6 EV times something. I don't remember this horrible equation from somewhere. Like horrible flashbacks to like first year chemistry lessons, but yes.
Yeah, so we have this limit, and that's your Lyman limit. And we know what wavelength your Lyman limit is when it's emitted from the source, if you're right there by that source. And then, so what we can do is we can make an observation of a galaxy, and then we can see where your Lyman limit is effectively. Just as you were saying, you know what elements look like, these sort of the shape, so to speak, of these spectra, and then they get shifted. And so what you can do is you can look at, we know
where it should be.
Exactly.
Where we think it should be, and then we see where that gap between where it has gone to.
Exactly. And then we know approximately, or we think we know how fast the universe is expanding. And so we use those two pieces of information and we calculate how far away the galaxy is.
I was going to ask about that. I guess to do these calculations, some model of the universal expansion rate must go into that calculation. And I know there's been a little bit of consternation recently about the potential us having some of the rates potentially wrong. So how does that feed in?
When you're doing these observations, you're working off the assumption that our Hubble constant is correct, or it's pretty close to correct.
That's upstream stuff. We don't worry about that. That's somebody else's problem, I guess.
Yeah, exactly. But of course you kind of have to do that, because if you're worrying about every single little problem, well, we could work this all the way down to, well, do we understand quantum mechanics well enough to say this? You're going down a rabbit hole. You got to build your house of cards on someone else's cards.
And I guess in some senses, although of course if that expansion changes, we'll update our results. At some point, if you've used the same process over and over again, you can get an idea, even relatively, that these are further away than the ones we've seen before. Even if we can't get a perfect absolute value, we can know that these are further away relative, at least, which is because they're all in the same universe, and unless it's got some weird boundaries where it's expanding at different rates, which makes no sense, then we're probably good to go on the relative measurements, at least.
Exactly. And that's exactly, anyone who is thinking, oh, well, maybe we're wrong, maybe it's not actually, fine, maybe you're right, but it still doesn't change the fact that this is the furthest back we've ever seen into the universe. And there's good reasons to believe that our Hubble constant value is pretty solid.
Yeah.
Most likely these numbers are correct. And even if they aren't exactly right, they certainly, the relationship between the values is correct. And it's pretty exciting because, as I said earlier, like, we're gonna have to change the definition of high redshift. Before this week, the highest redshift that anyone really took that seriously is about redshift 7, which corresponds to about 1 billion years after the Big Bang.
So we've already gone back to it looks like it quartered that sort of time from the Big Bang, if we're talking about 250 million years or so.
Oh yeah, it's unbelievable how in 1 week our universe has gotten, well, not our universe, we knew our universe was that big, but our ability to see into the universe has just expanded. It's been a really exceptional week. As a scientist, especially as a scientist who focuses on the early universe, it has just been a once in a lifetime week. Which
That's the
there's been a
problem.
lot
It
of
seems like with JWST, that's going to be, we say that, and then the next week comes along and it's even, it's just as good for some other reason, some other science program that's going on, and then the next week is just as good. And we really are at that stage with this amazing new instrument that we're just finding so many things out so quickly. It's like I said, it's like drinking from a garden hose at the moment.
Yeah, I mean, actually, you know what? I just said, like, oh, it's a once in a lifetime thing. And then I remembered, oh, wait, LIGO.
Oh,
I remember in undergrad, a professor came to our Society of Physics students meeting and gave a presentation on LIGO. And he was like, we're pretty sure it's going to work, but who knows when we're going to see this? Who knows how often, this is really hard. It's still da da da. And now it's like, oh, cool. LIGO saw another, neutron star merger. Saw another black hole merger. Yawn. Wake me up when they have a black hole neutron star merger.
When it becomes like passe like that, you've got a good instrument that's because it's making these things so commonplace.
Yeah, so JWST I think is going to become very similar to that, but it is still unbelievable, and it's unbelievable because one thing that's really exciting about LIGO is that LIGO really strongly confirms our model of general relativity, and it helps give us this idea of some populations of hard to observe objects. Very exciting in that sense. What's really amazing about JWST is that it is showing us stuff that we don't know how it works. We don't know, and what it's observing is it is really testing our models, and it's giving these really strong constraints because our models have to be able to explain not just more recently formed galaxies. It has to be able to explain these super early universe galaxies.
So if you don't mind, I'm sorry to cut you off, but I've got a dedicated section to that. If you don't mind me just keeping that on the back burner, is that okay?
Oh, of course.
Because we're going to definitely go into the theory stuff when I just sort of clean up this these redshifts. So we said that a lot of these things are still preliminary when I can speak. They're still candidates, and we need follow-up studies to do the confirmation. So what is that? Is that taking a full spectrum of these stars so that we've got multiple of these lines that we can they all look like they line up properly? Is that sort of the idea? That seems to be. I saw Jane Rigby saying, like, this is the gold standard. We need a full spectrum and these kind of things. Is that what's going on there? Is that the idea that we need multiple confirmations that kind of show the same pattern?
Yeah. So if you're only looking for one spectral line, it's a little bit easier. Sort of, if you're trying to take a photograph of really, really high detail of one little thing, way easier. You just focus your lens right there and you got it. If you're trying to take a really detailed photo of a lot more things, you have to think about a lot more aspects, right, in order to make sure that everything is in focus. Similar here, where the benefit of the Lyman break observation technique is that you're looking for one line. You're looking for one thing. And for follow-up studies, we do need to do complete spectroscopy in order to see all of these lines, make sure all of these lines are shifted in the way that
you would expect if you're going to put one value of redshift on it.
Exactly. I want to be very clear. These Lyman break observations are fantastic work. I am not casting aspersions on them. No. Even the people who made those observations recognize that there needs to be follow-up. And
as scientists, we're like incredibly conservative about like just the way we speak when we say there's uncertainty and we're not sure. A lot of the time we have very high confidence or it's a high probability, but we really have these high standards of evidence, 3, 4, 5 sigma in my field that we, before we start talking about things like confirmation and, being happy with these things, we need to reach these limits. So it's, it's just being careful about what we confirm too early.
And what I do want to point out is that if follow-up spectroscopy doesn't confirm these redshifts but finds a different result, that in and of itself is exciting because that means that these relationships are a little bit different in the extremely early universe. So it also isn't a failure.
Yeah.
It wasn't a failure of these groups. And to be super, super clear, they are reporting on what the Lyman break results are.
Yeah.
And so that, if the follow-up spectroscopy finds, wait, no, it actually looks like these are a lower redshift, they aren't quite that old, that's still an unbelievable result. This is still unbelievably useful science. So very exciting time. And I always, there's part of me, it's like, oh, I gotta be precise that this is preliminary, that we don't have confirmation. Yeah. But I also need to be clear that that doesn't mean that these results aren't incredibly
not super cool. Yeah, exactly. You got to keep that.
Exactly.
You got to keep that balance. The thing that really strikes me, and I just find really, really cool, is that you've got this sort of general or special relativity sort of conjecture that this physics is the same 35 billion light years away into the universe, and from something that was emitted 13.5 billion years ago, and yet you can make observations based on the physics being the same over those like ridiculous timescales and ridiculous distance scales, and it seems to give you sensible things and sensible results. I just find the idea that we have these rules that hold across those sort of scales mind-boggling, to be honest, and quite amazing that we can find these fundamental ideas out about our universe and they hold so well.
It's amazing because we are primates that had weird knees. Is like kind of the leading theory is that that's literally where all this came from, is that our knees locked. And so we walked upright and we had hands free, and it changed how we had, all of this comes from some like monkeys with weird knees. And all of a sudden, and then we developed math more or less to track, ownership of grain or whatever. And now we're able to understand how,
so never downplay the people who catalog grain. So from now on, because you never know where it's going to lead.
Oh yeah, lasers and all of these different things that we use now for all these observations mostly were made as just kind of like, we kind of need this for an experiment. It's a lot of work, kind of silly. This is going to sit in a basement forever, but whatever. We're just curious about this one thing. And then they get repurposed. So, and I guess math turned out to be like that. It was made for one thing, and there's an essay I really love called The Unreasonable Effectiveness of Math. And I forget who wrote it, which I'm a little embarrassed about. But
I can look it up. So what is it? The unreasonable
effectiveness of math or mathematics.
Right, of maths was written by Eugene Wigner.
Yeah, and it's I believe he was a physicist.
Yes.
And to me, it's such a great essay because it is completely ridiculous that math works.
Yeah.
And this is the sort of thing where I don't have a problem with people questioning the book. Wow, that's wild that we're able to model it. It's just, it stands up. That's the thing that's wild, is it stands up to observation. It does such a good job of describing things. This is my day job, and it still is unbelievable to me. It is so cool.
Those are the most amazing findings where you run the maths without ever having seen the thing. You run the maths, you work out that something should hold. Dirac does it for fermions, or they do it for a Aharonov bomb effect or whatever it is. And then they go look for it and it's actually there. It's like amazing that we have this framework this language that we can use to actually make predictions about the underlying nature of the universe. It really is an incredibly cool thing. So, and I'll make sure all of these pop up so people can see them, and all the links in the description as well, so people can have a look at those.
I mean, you're a particle physicist. It was pretty early. It was actually, oh my God, it was 10 years ago. It was 10 years ago, the Higgs announcement.
Yeah, I've got my t-shirt on. Yeah, I was there a couple of weeks ago.
Yeah, it's unbelievable. Like, that was one thing that was really incredible to me, is that these decades of building up the Standard Model, and it actually worked. Like, it was actually there, and it wasn't just there. It wasn't just, oh, we thought we saw it once. No, it was, as you said, 5 sigma. It takes longer than the age of the universe for that to happen randomly through random chance. That's why 5 sigma is the gold standard. And it's just, so yeah,
yeah, but now we're pissed off with the Standard Model because we can't break it. We know it's wrong, but we can't break it. So
break. That is so like at the sidebar. I'm sorry to get distracted, but that is so frustrating. Why won't thing break because we need it to break because it please break.
Just refuses
that is
to
one
break.
thing. That is one thing I would, I hope with social media, people are becoming more aware of this. Scientists want to be wrong, especially theorists. We want things to go wrong. We want things that contradict our models because that's how we can make better ones.
Yeah.
It is,
usually if you can find out a load of errors and sort of correlate how they relate to one another, you can start to nail down potentially where the error is coming from. I guess it's like when you do coding, you're like, oh, the code goes wrong in this way. Oh, and in this way when I do this. And how are those related? Oh, well, they both have, a variable that's in function 5 or whatever. You can sort of nail down where the problem might be. Whereas if you don't have any sort of bits that break, you're like, where do I go to get the sort of new stuff and the new ideas? So errors are not, or things that we can't understand are things that we really want to find. It's not something that we should be concerned or worried about.
Yeah, I mean, as a theorist, the most exciting day is probably when a model of yours gets experimental or observational confirmation. And the second most exciting day is when it doesn't.
When they find an edge case where it no longer works. Yeah, exactly.
Exactly. So, and that's part of why, again, if full spectroscopy gives a different redshift result than the Lyman break, that's exciting. That's cool. Yeah. That is cool information. Why did these two things find different answers? And we have to look into that.
That would be weird that one like elemental line shifted different to another. That would probably be something very, very interesting. So
it would be. I'm not saying that I'm expecting that. I'm not really expecting that, but it would be neat.
It would be cool.
It would be cool.
So when are we? Is there any idea of sort of a timescale for the confirmation, the follow-up spectroscopy? I guess was it not taken at the same time, or is it there and it just hasn't been analyzed yet?
So I am not part of the JWST collaboration in the sense that I am not in one of the research groups that gets that early release data, that gets first rights to the data. So I do not know, and I don't know if those who are in that collaboration can tell us. It's a little bit like CERN in that way, where you can give general strokes, but I would guess that the follow-up spectroscopy will be within the next year, but I can't tell you if it's going to be in the next month, 2 months, because the thing is, as much as I would love to hog JWST entirely for high redshift,
we're gonna ask you at the end where you would point the thing if you were the JWST god. So
I've been, I'll think about that one. Put that in my back pocket, and
all right. Well,
hopefully I have an interesting answer. But there's people that are going to be using JWST or have been using JWST to look at planets to understand planetary systems. People are using it to look a little bit lower redshift, the more local universe, to understand more detailed things about star formation and what have you in galaxies. So, I don't know how long each group, and I think to some extent that the follow-up proposals, because you have to propose for time and a target with these telescopes, with these observatories. I think a little bit who gets awarded that and when they get awarded it depends on what everyone's finding. We're finding unbelievable stuff in high redshift, in the high redshift universe. But what if the planetary people find even more unbelievable stuff? You know what? They're probably going to get higher priority. So I think that's a little bit tough to say, but I would say within the next year or so.
I think that's a really good setup they've got. I think like the next year is planned out, but then obviously, like you say, if we find some amazing signal coming from a nearby exoplanet, then obviously people are going to want to jump on that or whatever it might be. So I think they have the like yearly review, don't they? And it's like blind and based on the science proposal. So the next question I guess I had was why are we getting this kind of glut now? Obviously it's related to JWST. So is this the fact that we just have a bigger telescope with a bigger mirror, so we're collecting more light more quickly? We've also got this ability to look in the infrared, so we've got this more stretched out red light that we can now see because we're away at L2 and it's got the super cool telescope. Is this the idea that we've basically just got the ability, the technological ability to look further now? Is that the idea?
So my answer for this one, unfortunately, is little bit boring, but
That's all right.
you did such a good job explaining. You did such a good job explaining it.
I've got to try and make sure that like people understand that I know a little bit as well. I know it's all about the guest, but I don't want to just sit there like a nodding dog going, "Yeah, amazing, amazing."
Yeah,
so,
but you're exactly right. And the thing is that we didn't just put it out at L2 for fun,
for the banter.
Yeah, just like, I don't know, guys. Like,
Gaia needs like a friend out there. Let's
seems lonely. Yeah. We love throwing things in space that we can't repair. Just not our issue. And
Yeah, exactly.
We didn't just put it out there for that reason. We put it out there because there's lots of things that you can do if you're further away from Earth. You're in a colder environment. It's darker. Yeah. And there's a lot of equipment that you just can't stick on a geosynchronous or whatever, close to Earth orbit. You can't put that on there, because for just going back to the photography example, if you have too much light, you're going to overexpose your photo, and you're going to lose the details. And so there's a lot of instruments that are able to work on JWST because it is all the way out at L2. So Hubble is an unbelievable telescope. We have gotten unbelievable results. And, it was the Hubble Deep Sky Survey, which is what gave us that first look into again, now I feel like such a clown being like, the high redshift universe. Like, okay. You're impressed.
Everything's relative. Everything changes with time. No, we understand. Yeah. I've seen all the memes of like people looking at it and being like, high redshift universe, and it's the kid from the royal balcony, like what the hell is this now? Because it's just not. Yeah.
I mean, it's so true, because again, literally 2 weeks ago, you saw a paper on arXiv, which, for anyone who isn't familiar, arXiv is a website where people can post the preprints of their papers for people to look at. It's important to note that those papers have not undergone peer review. Usually they will say once they've been accepted, but it's something that people can look at and peruse. For scientists, you look at arXiv kind of the way that you would check like the daily news. So,
and I guess people like, I know, like, I don't mean this any slight on scientists at all, because this happens in particle physics as well. But whenever there's something big comes up or there's something new, there's a race to get on arXiv. We call it ambulance chasing in particle physics. There was a small, 3 sigma signal, or of maybe a new particle, or there was a couple of months back there was a hint that maybe the W boson is a little bit heavier than the standard model predicts, and then it's like 5, 4, 3, 2, 1 explosion on arXiv of theoretical ideas and potential observations, or what should we be looking for, because people are interested, they want to plant a flag, they want to be the first on it as well, which maybe that's not like the most scientific thing, but at least a lot of focus goes into the interesting new things straight away.
Absolutely. And it is worth pointing out that our culture in science of naming things after the first person to find them rather than like, okay, you guys all saw this at within 6 months of each other, fuck it, all of you have your name on it, good job. Actually, there's a great, can I tell one of my favorite stories really quick? Yeah. So Dr. Wu, so she was a Chinese physicist.
She's the CP violation one, isn't she? So,
yep.
You're talking. You're in my ballpark now. You're an LHCb ballpark.
I used to do particle physics.
Oh, right. Okay. All right. Good. Right. There we go.
Yeah. So,
excellent.
Dr. Wu observed evidence of CP violation, and she did this pretty close to around Christmas. And all of the men, and for context, this was in the early 20th century. So this was an era where there were very, very, very few women in doing physics. I mean, for Cecilia Payne-Gaposchkin had to come to the US to become a physicist because in the UK, she wasn't allowed to study. Emmy Noether lectured under Hilbert's name in Germany for a long time. And then when she was like, all right, I'm going to be a professor here, they're like, no, you're not. And Hilbert was like, well, she's been a professor here effectively for several years. So clearly the sky didn't fall. But anyway, Madame Wu, Dr. Wu.
Just leave her. She's doing fine. Like we don't need
She's
to worry.
doing great.
Yeah,
She's gonna figure out the most beautiful theorem in all of physics. Y'all just let her do her
She's
thing.
good. Let her be. Yeah.
But so Dr. Wu found evidence of DP violation, and this was pretty close to Christmas, and a lot of times, and this is true to this day, where the field kind of becomes a little bit dead, like a little bit before Christmas until after New Year's, right? Because people are with their families, everyone needs to take a break, whatever. But these guys heard that she had a result, and they all booked it to the lab. In order, part of that was just being like, we're not letting her get one over on us. But part of it, they would have done it for a guy too. But there is a little bit of a funny bit of like, we're not letting that Dr. Wu get this. So, but it's a very real thing. So this has been going on for,
Yeah. There's a very, people don't maybe realize it, but there's a very, very sort of competitive air as well as the collaboration. People do really want to get their sort of name on. So this is why I always find it really hilarious when people talk about like, captured scientists and, everyone's hiding the results about climate change or whatever it might be in science because there's one narrative. If there's one person in the room who knows the truth and can get a Nobel Prize, you better believe that they're running to the lab to post about the secret thing that nobody knows about. That it would be impossible. There's such a competitive nature in these collaborations.
I mean, also scientists are the worst people in the world at not talking about their work. Yes. Again, another fun little bit of physics history is the LIGO results got leaked a little bit. Like not leaked like to the broader community, but people got word about the LIGO results several months before the announcement because a guy kept telling his Tinder dates. I'm gonna be
what a lad.
I'm gonna be super honest. I'm
gonna win a Nobel Prize by that. Yeah, sure you are, mate. Sure you are.
I mean, I'm gonna be honest. A guy who liked me that I had known when I worked at CERN told me about the Higgs announcement a couple months before it happened. Just it's long enough in advance. There were a lot of people who work at CERN. So I'm not identifying anybody, but it's a thing that which is part of like, man, honestly, if they were able to get a conspiracy to work, good for them. How did they figure it out? Because like there's EHT honestly might be the best at keeping that stuff locked down. The Event Horizon Telescope might be the best at keeping stuff locked down because I haven't come across too many EHT leaks, but like, man, we are not good at keeping our mouths shut. So honestly, if they could train the rest of us in like a little bit keeping lip zip, that would be great because we are terrible at it.
I agree. So before we jump into the theory of why it's so important to find these things, the last question I had on the sort of the technical side was, is there sort of a hard limit? So we keep seeing these numbers going up in terms of redshift. Is there a hard limit to how far back JWST can probably look to the start of the universe? Is it either based on the technology of the telescope or maybe our ideas about the evolution of the universe? I guess, eventually you're going to hit just a big wall of plasma, but is there a wall before there that we probably can't see back beyond?
I think that's hard to say because JWST has performed so far past expectations that I honestly don't. You get to the era of reionization, and that's probably going to be
you can't do anything.
Probably going to be tough to go. Yeah. But if we're already at 100 million years, close to 100 million years, which again is a number that I've heard. I don't know how robust it is. Yeah. Again, my guess is that number is going to get moved a little bit.
The idea that we're even talking about literally an order of magnitude reduction in that time is a massive change.
It makes exactly. And this is where I'm going to be like a very typical scientist where I'm uncomfortable making a guess on how far back we're going to be able to see because again, it has performed so far past expectations that you're like, I don't know, man. Like, bro, I'm willing to say right now, we're probably not going to get down to order unity million years. Yeah. Probably not going to get down there. in terms of, do I think that we could break 100 million years? Probably. I mean, honestly, at this point, probably. What's that coefficient going to be on your, 10 to the 7? I don't know. I don't know what the coefficient is going to be on that 10 to the 7. But
and it's going to take a long time to look at all these things and see where they are and find. So yeah.
And part of what also makes that tough is that we're going to find more clever ways to use the instruments that we already have, because that's part of what happens is that people develop. The improvement on our observational ability isn't just coming from the hardware that we're building; it's also coming from the way that we analyze it.
Yeah.
So I would, at this point, and if you would have asked me this, 2 weeks ago, I'd be like, I don't know, I'd be thrilled if we got down to about 100 million years. That'd be neat.
And now we're like, now we've seen us get to there. Let's get back even further. Yeah. It's a moving target.
So yeah, my guess is it'll be something, some number times 10 to the 7 years after the Big Bang. That would be my guess. And honestly, that a lot of that is coming from the fact that you're starting to edge up on the fact that there is only, you're not getting past the era of reionization. You're just not. You're not.
This is what we always say in particle physics. There's the sort of joke about astronomers that they just deal in orders of magnitude, right? There's no precision.
Yeah. Why do you think I left particle physics? I hate keeping track of coefficients.
Oh God, like 10, 11 decimal places. Like I'm like, what is this? Like,
pi is 1, pi squared is 10. And that's most of what you need to know.
You can get shot in some places for saying things like that.
Well, the good news is that I'm in astrophysics now. That's fine.
So you can get away with it. As long as we're in the right order of magnitude, we're good
exactly.
to go. We're good to go.
No, that's something I love about astrophysics. This is actually a thing where, like, for my candidacy exam, it actually was like a thing. It was like, oh, hey, by the way, because one of my committee members was an observer, and continues to be an observer. She continues to be an observer. And another one is a phenomenologist, meaning, for people who aren't familiar with that term, a theorist who focuses on how to observe things.
How they would present in nature if their theory is correct.
Exactly. I am not one of those. I am the person like in the corner.
You sit in the quiet room saying, this is how it's going to be. Yeah, go work out the details of how we would prove this. Like, I'm hands off.
Exactly. And my advisor was like, you should probably figure out the units on your magnetic field. You should figure out how many Gauss that is. And I'm like, why would I do that? It's like, well, because you got people who care about those things on your committee. Go do that. This is because what I'm used to dealing with is ratios, right? But I like it that way. But yeah,
ratios are always good to get rid of the units. We like.
Oh yeah. They're great. Oh, they're fantastic. You're like, oh.
Right. So let's come into your area then, which is the theory of this stuff. So we understand why we're sort of seeing these things. We've got an idea of sort of how far we're seeing and how far we might be able to see. Why is this so important? Why do we care so much? Why are scientists so excited, apart from the idea of, it being incredibly cool to look this far away and this far back? Why is it so important for us to find these further off galaxies and these higher redshifted galaxies? What does that inform in terms of the science of the universe that we understand?
Everything. Okay, sorry. I just had to do that, but it is true. But I'm going to get into it.
What was that?
So,
did I miss something?
Oh no! I was saying everything.
All right. Okay. Good. Right. I like that. That gives us some good scope. That gives us some scope.
But getting more into it, all the baryonic matter in our universe, so not dark matter, actually exists in this unbelievable structure called the cosmic web. And the cosmic web forms largely out of the fact that things with mass get attracted to each other. That's gravity. That's gravity, baby. That's all. That's what it is. And you end up getting this structure called the cosmic web. And that is the structure of baryonic matter in the universe. So as far as we're concerned, pretty much everything that we're capable of interacting with in the universe fits into that structure. That structure is defined by how galaxies form and where they form and what sort of timing they form with relation to each other, right? And then how do they impact how other galaxies form? So that's going out in terms of the entire structure of the universe, really. Now, when you look more inwards, how galaxies form, that dictates where stars form and when they form and what kind of stars they are and how they live their little star lives. And then when those end, that tells us more stars form out of the corpses of their parents. I once said that during during one of my graduate courses on galaxies, and my professor was like, "You're correct, and please never say that again." Yeah. I'm sorry, Erica, I just said it again. But it's true, and eventually you start getting planets forming out of those stars. Yeah. And then you end up getting planetary systems and solar systems, and eventually you get planets forming around tiny itty bitty stars. Our star is about as small as you can get a star, and that's why we're able to evolve for so long, is because the smaller the star, the longer the life. And so that leads to, how can you find planets that are in a system that is stable enough that life can evolve, that more complex things can evolve? So, and that all goes down to, how does a galaxy form and how does a galaxy evolve?
So we want to understand that sort of history of how the first stars formed, and then how did they go on to form the next series of stars, and then how did the galaxies come out of that, and then how do we get the galaxies that we had in the early universe, how did they become the spiral galaxies like our own with planets and these kind of things. So it's really understanding that whole history. By looking further out, we're getting further back in time, and therefore we're getting more sort of epochs in our models, and our better understanding of basically where we come from, I guess, is kind of what you're getting at with that.
Exactly, because one thing that part of why astrophysicists don't worry very much about constants is because what we're talking about, a million years is nothing. A million years is that in terms of the systems that I study. 10 million years is nothing in terms of the systems that I study. 100 million years, now we're starting to say that's actually something that's like a decently long time scale. But as a result, we can't just sit here and say, I'm going to look at that galaxy as it evolves. I mean, I guess you can, but man, you're going to need good documentation, because it's going to be a long time before that thing changes. But what's amazing, what's really, really cool about the fact that the speed of light travels at a constant, that photons travel at a constant speed, the speed of light, means that we can look back in time. And so I can't watch one galaxy evolve, but I can look at other galaxies that are further back.
Different stages in their evolution, and get that whole kind of story, and with statistical significance. If you can look so far, you can get a nice statistical grouping at this redshift, and this redshift, and this redshift, and this redshift, and this redshift. So you can kind of start to get that sort of flick book sort of idea of the evolution over time.
I love that flip book. I'm going to steal that. I will credit you if I'm using that.
Well, we can't, it's quantized, right? You're not going to get every single one in every dot, but that flip book seems sensible. I don't know, maybe.
Because that's a great metaphor, because the thing is that I really want to drill home for people is that we are alive for less than a split second in cosmic times, in cosmic time scales. And as a result, we have to try to learn all this information about the universe, only taking a slice. Imagine if you paused every human on Earth in order to understand how humans grow. You couldn't just follow one person. You're effectively looking at it for 1 second. So you'd have to look at younger people, different people, but younger people. And that's part of also why it's hard for astrophysics to have the same statistical significance that particle physics does. Like, it's hard to get to 5 sigma when you have to look entirely at different things. But that's part of what's so cool, is that we're looking all the way back to see how these things formed in order to understand how galaxies closer to us also formed. And, for people who, as a sci-fi nerd, especially as Star Trek, especially Star Trek, because it's the generation shift. But this is super far out. It is not in our lives. We do not have any. We are not going to be able to ship people to other planets anytime soon. because there's a lot of
even though Elon says we can, we're just not, because he's just talking rubbish.
Well, okay, he thinks that Python is the best language for machine learning, and I'm like, you are talking, or for artificial intelligence. For artificial intelligence, like you're talking, what you actually are talking about is a very small number of machine learning applications, and that is not the entirety of artificial intelligence. And people say, Hannelore, you're very boring at parties. I say, yes, and that's why I don't go to very many of them. But you know, eventually, long scale, whatever. And I'm not saying that this is the reason why I study what I study. I study what I study because it's neat. Yeah. That's the answer. But the reality is that this sort of information allows us to better determine what would be something to look at, for example, for habitable planets, for where are these going to be. If you just take a telescope out and you point it at the sky, you're going to get a lot of different things. And once again, walking back to that photography analogy, sometimes you have to use different lenses to be able to focus at different lengths and focus in different amounts of detail. So if you take a look out into that galaxy, that's like you just have your standard, you know, you're holding up your smartphone, taking a picture. But if you learn to figure out, oh, hey, areas that have this kind of dust with these sorts of chemical properties, that's more likely to host planet or host a solar or planetary system that's this age and has a star of this mass, then you can use specific filters on your telescopes to be able to better look at that. So in a lot of ways, it's hard to answer the question of what do you hope to learn, because we're hoping
to learn everything about how the universe evolved, and therefore there's so many things that we can hone in on that and have with that better understanding.
And ideally, we're going to learn stuff that we don't even think about, that just hasn't even occurred to us yet. Totally novel things. How do you imagine a totally, you know? So, but yeah, and I know that sounds a little cheesy maybe, but legitimately looking into the super early universe allows us to understand how literally every single thing
came forward from there. And what are the current theories regarding how the galaxies evolved in the history of the universe, and kind of how they led on from those early galaxies to the ones that we see today? Is there a kind of standard model, to use that term again, of what we think happened? And did the results that we've seen so far for the new redshift regime, do they challenge that? I think you mentioned that they might do when we had an initial chat offline.
So there is both a lot of agreement on the broad strokes, and there is almost no agreement on the details.
Yeah, I mean that's normal, right? That's fine.
Yeah. So in general, things that we all can agree on is that there is a supermassive black hole at the center of pretty much every what we call normal galaxy. Some dwarf galaxies, which are shockingly just little guys. They're just little galaxies. Some of them have what we call intermediate mass black holes, which are black holes that are about 10 to the 4 to up to 10 to the 6 solar masses. And then a supermassive black hole is 10 to the 6 and up. So you get your big black hole, you get your big boy. And to some, I think pretty much everyone agrees that you have some amount of a proto-galaxy that has developed. It's not that you have this black hole and then everything sort of randomly comes to it. There is some amount.
So this black hole, did that come from an initial massive star, and then we go forward from there? Is that sort of the idea, or were they?
We knew. Actually, no. I'm glad that we don't know, because I really like this as my career. But we don't actually know where that black hole came from. And that's one thing that I'm really excited about is I think that JWST is going to help us rule out formation models.
Okay.
So what the details that people disagree on is, how does the black hole form? We disagree on how much of the galaxy was formed. Some people think that you pretty much had, an elliptical galaxy, and then the black hole just kind of slid down to the middle of it. Some people think that you just had, sort of the parts of a galaxy, and the black hole helped all those parts kind of fit together because of its gravitational force. And that's something that JWST is going to help us answer, is what is the actual assembly history of galaxies? First of all, what is the order of these things getting put together?
Yeah.
And part of what I'm really excited about is I study how supermassive black holes grow, I study how they form, and I study how, as they're forming and growing, how they impact the galaxy around them. And these ultra, ultra, ultra high redshift observations, that is really helpful because we haven't, before the JWST data got out, our highest redshift, really reliable observations were about 1 billion years after the Big Bang. A little bit less, but about 1 billion years. And that was already hard enough. Our understandings of how black holes grow, we already didn't know how those got big enough fast enough.
Yeah. So you had a cap in time, but you didn't know anything before that. It's like, okay, we have to start here because we can't see any further back. So you sort of got you're looking at a model of how something evolves, but you can't see back further than, some hard cutoff that,
And so, what you do is you make all these different models and you try, and then what the phenomenologists do is they try to figure out what would be different things you could tell about them, almost like a forensics type situation where you try to say, okay, what are the signs that this thing happened so that you can say, okay. And what's really exciting to me, to everyone, but especially me from my perspective of the type of researcher that I am, is that is such a tight time constraint. Let's say that, we're about 250 million years after the Big Bang, right? That you have a galaxy.
Yeah.
If that galaxy has an intermediate mass black hole at its center, and I'll explain in a second how we can tell that, that's really cool. And that tells us that the galaxy assembles.
Yeah.
It's much more assembled.
Yeah.
Yep. And so the people that are saying, okay, you mostly have a galaxy and then the black hole kind of like whoop, in the middle of that, that's a little bit leaning that way.
Yeah.
If you have a larger black hole, so there, in general, right now, up until we had JWST, when you pointed a telescope at the sky, pretty much everything that we saw followed a relation of your black hole is about 1/100th to 1/1000th. Your central supermassive black hole has a mass of about 1/100th to 1/1000th of the mass of all of the stars in the galaxy added together.
So there was a sort of ratio that, with some wiggle room, but a well understood sort of ratio that you expect to see between the mass of the central black hole and the mass of the constituent stars and baryonic matter.
Exactly. And so if there's an intermediate mass black hole at the center of these ultra high redshift galaxies, first of all, that intermediate mass black hole is a smaller fraction, because we do have an estimate of the total mass of stars in those galaxies. And it's about 10 to the 9. It's about 10 to the 9 solar masses of the total mass in those total stellar mass in those galaxies. And so either you have an intermediate mass black hole, which is smaller than you would expect from that relation that I was talking about, which then would tell you that, again, it looks like galaxies form substantially, and then your central black hole, what we call the galactic nucleus, kind of slides its way into the center. And, if, on the other hand, we have a supermassive black hole at the center of those, that implies that your black hole gets really big pretty early on in the assembly history. And that also means pretty exciting things for people who work on accretion theory, like me. So accretion is the way that black holes grow. And right now we know that our models of how accretion disks work are broken. That's why I have a job, is figuring out how to fix those. But the question is, are we most of the way right, and there's just little tweaks that we're not considering? Or are we super not thinking about a lot of physics that's going on? The question is, are we missing little bits of physics, or are we missing lots of physics? And if we have a supermassive black hole at the center of these ultra high redshift galaxies, those are forming they're forming in less than a third of the time, a quarter to a third of the time that we previously thought we had. And that means really interesting things.
That means that our models were wrong, which is always interesting because we have to go away and have another think.
Oh yeah. And then why that's cool, I'm about to get to the rest of the galaxy, is that how those grow influences how radiation is getting kicked out of those accretion disks and going out into the galaxy and shaping how stars form. And then that in turn shapes how pretty much everything else in the galaxy is forming. So either way, we're going to find out some wild stuff about how galaxies form. And then that will give us some insight into how groups of galaxies form. And then, again, so insight into both the largest scales of the structure and the smallest scales of the structure.
It's really, really interesting. And like you say, it's basically everything, because without that story going forwards, there's no us to look back and see what that story actually was. So it's incredibly interesting. So yes. so that brings me on to the kind of last question I had on this, I guess then, that is, where would you be pointing JWST if you were the queen, the goddess here, and deciding where we're going to point JWST? Where would we be looking to work out these things about the black holes and how they influence the galactic formation and evolution? Or maybe you would just be like, nah, I want to look at exoplanets. Where would you be pointing JWST if you had the chance?
I would wait until, so first, before I would answer this very specifically, I'd wait until we had spectroscopy, and then I would see where's our highest redshift galaxy, and then I would point JWST at that and do a really long exposure. Yeah. So just like with photography, you do a longer exposure, you're going to pick up more things, you're going to pick up fainter things. Yeah. And because where we have that super early galaxy, I bet that somewhere around there's going to be even earlier things. Because I want to see how early we get. And I also am hoping that we then could see some of the first stars, because that would also be
about that, actually, because you're right. If there's something that's super far away there, then the stuff around it, you would imagine, is related to that thing. So like you say, if you expose more, maybe you start to see the things that are related to it, maybe a little bit older, which are around it. I'd never really considered that kind of idea, but it makes naive sense to me.
Oh yeah, and because the other thing is that galaxies, they don't form isotropically, right? They cluster. And it would be really interesting to see, first of all, are our oldest galaxies, are we finding them kind of all on their own? If so, that's a really interesting thing. It means that the galaxies have to migrate a lot to get to these clusters. Yeah. Be interesting information on its own right. But I'm guessing that it actually would be, a bit of a cluster situation, and you would have even older, but therefore fainter galaxies, or galaxies that are now older. At the time, they would be probably younger, but it's a little bit hard because it's the oldest light, but they were emitted from the youngest galaxy. But you get the point. So that to me would be where I'd want to point it. And that's actually how we first got these observations of the or what we called at the time ultra high redshift universe, was the Hubble Deep Sky Survey, which is they just took Hubble and they somehow convinced, the committee that runs Hubble, say, hey guys, let's just point this in one spot for a couple weeks. Yeah. And we're just going to leave it there. And we're just going to see. And somehow they convince people, because Hubble, the Hubble time is so precious, right? Yeah. Everyone wants it. And so I still want to know what magic they worked in order to convince them. Just point at the spot and just let her go. But that's how they first observed these really early, really early universe objects. And so I would love to eventually see JWST do something similar. And to me, the way that you pick a really interesting spot for that is you look at what, where's the oldest thing we've seen? Yeah. All right, let's just take a look. Because there's going to be interesting information there either way. So that's what I would love to see.
Sounds like a really, really good idea. Hannah Laura, thank you so much for going through all that with me. That was really, really, really interesting. I've seen all this sort of hullabaloo this week, and that's sort of nicely explained to me what the hell's going on, rather than them just being really, really far away and really, really red, and it's really put the science to it. So thank you so much for taking the time to go through that with me. I really, really appreciate it. Is there anywhere that you'd like to point people to, first of all, find out more about this work and what's going on and the new things that are coming out, and also your work, your socials that we can point people to?
Well, first of all, thank you so much for having me on, Sam. I love talking about this stuff. And so yeah, my Twitter and Instagram handles are Joy of Physics.
They'll be down below.
And for both of them. Not on TikTok at this point because I'm like, is there any new social media at this point? I don't know.
I keep being told to like get a TikTok account, and I'm just like, I can't. I've got too much on as it is, but I think I might get roped in eventually. But we'll
That's
see.
sort of how I see it. I'm like, you know what? Let's get some papers out before. I'm going to be super honest. Some of the best and most up to date science communication that I'm coming across is on Twitter, because it's scientists getting out there explaining these things in their own terms, and you're able to interact with them and ask them questions. So very sincerely, if you want to know more about this, I say get on Twitter. And what I do, what literally even how scientists learn about stuff that they're not experts in, that aren't in their fields. How I learn about exoplanets, for example, is I have some friends who are exoplanet researchers. I follow them. Then I see whose stuff they're liking, who they're retweeting, and then I go and I follow them. And that would be, my recommendation. I'm not saying that's self-promotion,
No.
But it's absolutely, to me, if you want super up-to-date, science communication on this and the ability to talk to scientists and ask them for clarification, Twitter to me is the best spot to do that.
To be fair, that's where I found all the excellent people I've been talking to about JWST. So I think that's a very good suggestion. It's easy to filter, and like you say, you can interact with them. People write amazing threads about all these new findings, and usually you can literally get. They obviously cite the paper, cite the scientist. Usually, 9 times out of 10, that scientist is on Twitter discussing it as well. So you can really sort of get to the experts, as it were. So I think that's a really good suggestion. Hannah-Laura, I want to thank you again for taking the time, especially on a Friday afternoon. I'm going to go get some dinner now, but I've really, really enjoyed that. And let's stay in contact. And then when the next amazing thing comes down the pipe, we can get you back and have another chat about it.
Absolutely. This has been super fun, Sam. Have a great night.
Thank you so much. I'll talk to you soon.
Okay,
bye now. Bye. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.